Hello class, today we're going to talk about ionic solids, metals, and alloys. A very important topic we're going to be talking about is the atoms and ions, how they form molecules, and we're also going to be using Coulomb's law to describe how they're going to be arranged. So a particular representation is a way of showing something that you don't really see in a model. And if we take a look at this cubic structure for salt as an example, salt has a positive charge with the Na and a Cl minus, but in this example, Cl minus is larger than sodium, and the reason is because one of them has a negative charge and sodium has a positive charge, which makes the atom bigger for chlorine, even though chlorine technically is smaller. And what happens here is they are attracted very strongly through these attractions, these forces, specifically plus and negative. Think of it kind of like a magnet. And what happens is we call these Coulombic forces, and they are arranged in an alternating and repeating pattern, usually called a crystal structure, or in this example, an array. And in order to have them attract, they need to maximize attraction and minimize repulsion. And the reason we do that is because chlorine-like charges will repel, just like in the chlorine example. However, with sodium, you have an attraction between Na plus and Cl minus. A particular representation here shows you how these crystals are formed. The positive charge is alternating with the negative, and this pretty much is going to apply for all ionic solids. And when we create these particles, we want to keep a couple of things in mind. Number one is the sizes. These sizes are going to represent, based off the element that we have, generally a negative charge is going to have a larger size, and because of the fact that they are adding more electrons to their rings, to their shells, not the rings, and that is going to help us determine what size is going to be bigger. The other thing also is they're going to be alternating to minimize the attractive and repulsive forces. Now let's talk about lattice energy. So lattice energy is a term used to describe how much energy it takes to form a crystalline structure. So for example, if I have an A molecule and a B, and I want to form a crystal, I'm going to need some sort of energy that's going to form those into an ionic compound. And if you actually have this, you can determine that that energy is going to decrease when these atom ions come together. So it's very similar to our potential energy diagram that we saw in the chemical bond for covalence, where if I actually put some lattice energy to break them, I can actually make the ions. But if I actually want to form the lattice structure, I'm actually going to have a lower potential energy, and there's going to be heat being released. So when ions are being formed, you are actually releasing heat in the form of lattice energy. And this is due to the fact that these attractions are going to be electrostatic, and they're going to have very high melting point and boiling points due to this attraction that we have there. So in a nutshell, what this really means is that if I want to break these ionic compound lattice structures, I have to put some energy in, or if I want to form a crystal structure or a lattice structure, I will be releasing energy. Now let's talk about some trends that you'll find, and I'm going to move this a little bit so you can see. This is a typical question that you're going to get. There is compounds that have specific lattice energies and specific melting points, and so your job is to take a look at what is the pattern that you'll find. So if we notice carefully, as the ion radius increases, meaning that size of that atom increases, the distance increases, which means that according to Coulomb's law, that is going to reduce the attraction, and as a result, the lattice and the energy decrease. So if we take a look at something, for example, like sodium fluoride that has a melting point of 988 but a lattice energy of 209, generally the higher the lattice energy, the higher the melting point you're going to have. And this also goes with ion charges. If you take a look at the ones on the right hand side, you're going to find that magnesium has a +2 charge while oxygen also has a -2 charge. Compare that to table 1. you're going to find that the lattice energy is much higher because of the ion charge according to Coulomb's law that states that the charge is going to also be a big factor in determining the force of attraction.